Hello, everyone. My name is Thomas Carnes. I'm a PhD candidate at Virginia Tech, and I'll be presenting on the performance of welded grid reinforcement as crack control in the end zones of pretensioned bulb T-beams. Just as a note, this project is sponsored by the Virginia Transportation Research Council. So a brief agenda, I'll go through an introduction to the problem, and then two testing phases, the first being tensile testing of smaller concrete specimens with our goals, testing setups, and some results, and then large-scale pretensioned concrete bulb T-beam or PCBT testing with goals, our implementation, and results, and then some conclusions and future work. So an introduction to the problem, these PCBT end zones are subject to large transverse tensile stresses, so in the up and down direction during strand detention and lifting operations from the pre-stressing beds. These transverse tensile stresses are caused by the point loads of the pre-stress distributing into uniform compression throughout the cross-section. As a result, cracks often occur, posing a durability concern. This allows for moisture ingress, increasing the chances of reinforcement corrosion, potentially shortening the lifespan of these structures. As it currently stands, the design codes often do not adequately resist this cracking. A little bit more into the motivation specifically for Virginia. Currently, the state of Virginia Department of Transportation, or VDOT, follows design tables that were created in the mid-2000s. The current methodology works fairly well, but there's a lot of reinforcement congestion and cracks still occur. So some of this reinforcement congestion includes bundled stirrups closely spaced at the ends of these beams. And then even when it's not bundled, the stirrups are still relatively closely spaced. This makes it hard to place all of the stirrups, consolidate the concrete, etc. In addition, even with that, a lot of cracking still occurs. So this leads to the desire to create designs with less congestion but still control cracking. A little bit into the motivation with welded grid reinforcement, or WGR as I'll call it. There are limited studies that suggest that using WGR instead of traditional rebar only may positively influence cracking performance. And as a note, WGR can be made of large deformed bars, so you can see that in the bottom right. It's not just your typical welded wire mesh you're seeing in like a driveway or something like that. And this was something our project sponsor was really interested to see. So our first testing phase was tensile testing. We created 14 of these specimens, which you could see at the bottom, with 4 longitudinal number 5 bars that are pulled in tension with 4 foot long by 10 inch high concrete specimen that was simulating half width of a PCBT web. 3 of these specimens had no cross wires, and the remaining 11 had cross wires of varying sizes and spacings, going from 3 inches to 24 inches. In addition, one of the specimens had hand-tied cross wires instead of welded ones to see if there's a difference with those properties. And we were looking to see how this cracking behavior changes based on the spacing of these cross wires, the cross wire diameter, and the longitudinal wire stress level. So here are some photos of 4 of the specimens that we tested. These are 4 different spacings of cross wires and 3 different cross wire sizes up here. So D4 represents 0.04 inches squared area of cross wire, D20, 0.2 inches squared of cross wire, etc. And just looking at these photos, you could see that the cracking pattern remains fairly similar for them all. There's not a huge difference that's immediately visible. So the next thing that we did was compare the stiffness of these. So we compared the average rebar stress, so the rebar stress outside of the concrete, compared to the percent change in length. We looked at different combinations of crosswire sizes, crosswire spacings, and there really didn't appear to be a trend of any of these positively or negatively impacting the stiffness characteristics, leading to the takeaway that cross wires, whether it was hand-tied or welded, it really didn't matter for the stiffness. And then we also looked at crack widths. So at the initial stages, the crack widths were determined using digital image correlation, and then at higher stresses, these crack widths were measured using crack microscopes. Again, we looked at similar combinations of crosswire sizes, crosswire spacings for both the maximum and average crack widths, and there were no observable trends. All of the specimens performed very similarly for maximum and average crack width, indicating that the crosswires really did not make a difference. Finally, we looked at the average rebar stress versus the crack width summation, which I defined as the sum of the width of all the cracks around the specimens on both sides. We looked at the same combinations of crosswire sizes, spacings, and there was no trend. So at least for these small scale tests, using WGR does not really seem to provide better results. At the same time, we were performing large scale testing as part of another project where we were able to implement some of these WGR grids into the end regions with the goal of observing the cracking performance of these PCBTs with varying levels of reinforcement in the end regions, and also observe the cracking performance of those with just rebar stirrups and those with WGR as end zone reinforcement, and compare between the two. As a note, the top right image is one of these welded grids that we had in the end zone, whereas the top left is traditional stirrups. The bottom left photo shows our beams getting lifted out of the casting bed, and the bottom right is the end of one of the beams after it's been delivered to Virginia Tech. So we looked at 6 different end zone reinforcement designs with different working stress levels. So the top 3 were 18, 27, and 36 KSI working stress levels for the stirrups in the end zones, just using traditional rebar. And the bottom 3, the first is 18 KSI with WGR and rebar. VDOT, the Virginia Department of Transportation, wanted to look at rebar used for just the shear demand and WGR used for the crack control. And then the other 2 were 18 KSI WGR only and 36 KSI WGR. As a note, the top left is the standard for this size beam with VDOT. And the working stresses were calculated using a strut and tie model that was used to calculate the current VDOT design guidelines. So here are some cracks that we mapped after the strands were cut and the beams were lifted from the casting bed. As a note, there are no cracks shown on the end face of the beam because this was covered with formwork, so we were not able to measure those. But this was within 1 day of casting. And then after delivery to Virginia Tech, you could see a lot more cracks popped up over about a month. So there's significant crack growth stemming from time-dependent effects, which some of the studies on these indicated and some did not. So just a quick comparison for one of the working stress levels between the rebar and WGR end zone reinforcement. You can see the cracks are fairly similar in location. The cracks for the WGR specimen are on average wider and have a longer total length, which is just the summation of all the crack lengths for the 18 KSI working stress. But the specimen with stirrups had a slightly higher maximum crack width, but very slightly higher. In general, the WGR specimen had a greater total cracking area, where the total cracking area was defined as the summation for all the cracks of the length of the crack times the width of the crack divided by 2, basically approximating each crack as a triangle. And we see similar results for the other working stress levels and comparisons. So for all of the specimens in general, we see that the average crack widths are nearly identical, within 1,000th of an inch. But for the widest crack width, we saw that the specimen with 18 KSI working stress levels for the WGR and stirrups combined performed the worst. And for the WGR only compared to the stirrup specimens, they each had a slightly smaller maximum crack width than their respective stirrup specimen. In general, as you would expect, as working stress increases, crack width also increased. Looking at the total cracking area, which again defined each crack as an idealized triangle and summed up for each of the cracks, the WGR specimens had a higher total cracking area, so more room for water penetration and things like that. In addition, we noticed for the stirrup specimens that the cracking area actually decreased as working stress increased, which seems a little counterintuitive. So it shows that all of these cracking properties do not scale linearly with working stress. So just some quick conclusions. The implementation of WGR does not appear to improve tensile cracking performance compared to traditional rebar, like some studies suggested. It doesn't really appear to negatively impact it either, though, and it's a lot faster to manufacture on site, so it could be a positive. In addition, the cracking severity in the end zones does not scale linearly with design stress. In the future, I'm doing a lot of finite element modeling of the results. On the right, you could see cracking models of some of the tensile testings. I'm finishing up the calibration of that right now and going to be implementing those models in the PCBTs to predict cracks and to analyze some other end zone cracking solutions so that we could develop design guidelines to appropriately address this problem.